So James Bagrow is an associate professor of mathematics and statistics at the University of Vermont. He's a member of Vermont Complex Systems Center. Before he joined Vermont, he was a postdoc at Northeastern University and also assistant professor at Northwestern University. So he got his PhD in physics in Clarkson University in 2008. And he mainly studied like trying to understand the underlying rules and organized principles of complex systems, physical and social. So he usually deals with large data sets and models to try to understand and explain these systems. And with emphasis on network science and human dynamics. Like today, he'll talk about information flow and prediction. So I'll stop talking here, and Jim, the floor is yours.
Great, thank you. That was a very nice introduction. So thank you everybody for coming. Thank you for having me. This is really exciting. I'm going to speak today about a project that we've got a couple of papers on trying to understand information flow and trying to understand all of the data, all of the digital traces or behavioral traces that we kind of leave behind as we interact online on social media and online social platforms, and try to just improve our understanding of what those data can say about us and what kind of insights you can infer from those data. Let me see, my slides are not advancing. Okay, everybody can see the slides. It's all looking good. Okay, great. So, we live in this big data era, and in the past 10, 15 years or so, there's just been an enormous rise in the amount of data in many scientific disciplines, and there's been a lot of data coming out of these social media platforms. So I have a quote here, for example, from Facebook Engineering, way back in 2014, where they were growing their data set at the rate of 600 terabytes a day. And it's probably even more now, probably much more. So there's just an enormous amount of raw data going on there. Platforms like Twitter average thousands of tweets per second, and even other areas that that act as communication channels, but are not necessarily public in the sense of social media, like these text messaging apps on our phone, an enormous amount of information. So there's a quote from an executive at Apple that said that Apple's messaging platform was peaking, and again, this was 6-7 years ago, peaking out at 200,000 text messages per second. And it's an enormous engineering effort to try to deal with all of that data, but then it's also raises a lot of interesting questions about that data. How much of it is kind of actionable information? How much of it is noise? I'm very interested in this notion of kind of information flow, and if we can determine, how well are people listening to one another? Are we all just kind of shouting at one another online? It certainly seems that way when you get deep into these social media platforms. But another aspect to this, of course, is that even if information is flowing between individuals at a low rate, maybe not very well, there's in principle a ton of information that's flowing from those individuals to the platform provider. So to Twitter or Facebook or WeChat or whatever kind of platform it is. And then that kind of begs the question, what can those platform providers say about their users? What can they predict about us when we interact with those platforms? And also, if we kind of opt out of a platform, say you don't use Instagram, let's say, can they still determine, maybe through other platforms, other sources of data, what can they still say about those individuals that are kind of outside of their user base? And of course, there's a lot of really troubling news these past few years of some of these platforms. Here's a leaked document from Facebook that said they were targeting emotionally vulnerable youths because they were more susceptible to advertising. And there's very kind of scary ethical concerns. And I picked on Facebook, but I'm not necessarily trying to single them out. And of course, in terms of this, what can we learn from this data? What kind of insights are available? We are also in the era of deep learning and machine learning and AI, and there's just tons of advances. It seems like every week there's some new major breakthrough going on, and all of these industry partners, Google, Microsoft, Amazon, all of them are really pushing the boundaries of frontiers of machine learning and AI to power their platforms and solve their problems. And do all of this research. So, for example, I saw a talk from Yann LeCun, who's one of the AI executives now at Facebook, a couple of years ago, and he said that every time they receive a new photograph on any of the platforms, and I think at the time Facebook was receiving 2 billion new photos a day across, Facebook and Instagram and all of these. Every time they receive one of those photos, they pass it through 2 deep neural networks, and they had some amazing statistic. Like every single photograph goes through one of those neural networks, and no photograph waits, I think, more than, it was like 10 seconds or 30 seconds by the time it's actually been processed. So it's not just that they're accumulating all of this information, they're processing it almost in real time, just with all of the fleets of servers and everything that they have. It's very amazing from a technological point of view, and it can provide all sorts of information, in this case through all this computer vision. And so out of this comes all these questions about information spreading. If we can start to understand how people are communicating with one another using these platforms, we can learn a lot about what they're talking about. But then also the double-edged sword is those platforms could be creating a very negative, having a very negative effect on communication. And of course, we're probably all sick of hearing about COVID-19 and the pandemic and everything, but there's a lot of talk now about the infodemic and the rise of misinformation, targeting COVID in particular, but also just vaccines in general. There was a study that came out yesterday, actually, about this. They call it the Disinformation Dozen, which is an amazing name. And they essentially found that about 2/3 of the anti-vaccine sentiment online on social platforms comes from 12 individuals, 12 people. And so there's a very scary kind of amplification effect that can occur with all of these social media. And there's a ton of research that people are going on in terms of like fighting the infodemic and trying to just better get a handle on these notions of information spreading and information flow. Here is an example of some studies, a by no means exhaustive list of kind of data-driven study of information spreading or information diffusion on social media, on mobile phones. I have a couple of papers where I looked at spreading around emergency events on mobile phones using mobile phone data. These tend to be what I would refer to as kind of structural studies, in the sense that they use a proxy for some information or some idea, like a kind of keyword or a URL, and they track that URL as it's been retweeted or spread or something like this. And there's kind of a gap, in my opinion, between those proxies and information, because you could imagine a successful communication occurring that isn't really spreading that kind of keyword that you're looking at. Likewise, on the other side of the coin, there's also been a very long and rich history of modeling information spreading. All of the kind of disease models, which are a lot of times in the news right now, SI, SIR, these compartmental models, you can also use them. Excuse me. You can also use them to track the spread of ideas or the spread of memes or things like this. And then there's all sorts of specialized models, complex contagion and threshold models, and consensus and voter models. There's lots of very exciting modeling frameworks for modeling this spreading. They when you try to connect those with data, sometimes there's a challenge, because they tend to model something that's kind of latent in the data, like there's a belief state or some idea, you've adopted a convention, or so there's something that isn't necessarily measurable if you start actually looking at all of this social media data. Now, one area that I've been interested in is trying to get at this idea of information spread by bringing in more from information theory. And information theory is the kind of mathematics of information, and there is a disconnect between the mathematics and our kind of common sense. You know, they take a different view of information, but I think that it's still actually very useful to try to incorporate those tools when looking at the data. I'm by far from the first person to ever consider that. There's, again, a very long and rich history of people using tools from information theory to study spreading. Here, I'm highlighting two very, very cool studies from a couple of years ago. One that was kind of looking at a measure of information flow called transfer entropy based on the timings of tweets. So if I'm watching users who are tweeting and I keep track of when those tweets occur, how predictable is the time at which they will next tweet or their upcoming tweets, given, you know, the times of their previous tweets and given the timings of other people's tweets. They've essentially taken the tweets and converted them into spike trains, this kind of events, and using tools that are actually quite common in applications like neuroscience, where they're looking at these similar kind of spike trains. And another study on the right was also looking at time series, and they were looking at time series of the volume of tweets, so the number of tweets that were coming out of different geographic locations, and trying to look for like information theoretic precursors of like sudden spikes in activity. So there was a protest that occurred in Spain, and they found a kind of groundswell of support for that ahead of time. It's a very, very cool study published in Science Advances. Now, neither of those papers actually looked at the tweets themselves. It was always either counting the tweets or looking at the timings of the tweets. And there's actually few papers, in my opinion, that make the effort of looking at all of the language data in tweets in particular. And I'll be focusing on tweets as well, because that data tends to be more publicly available. There's all the words, all the text, the contents of those tweets. There's a lot of information in there. So I think a good argument should be to like, let's look at those words. Okay, so how can we go about doing that? That's where some of the information theory can come in. Excuse me. Okay, so you can think of someone on Twitter who's creating a bunch of tweets as generating a kind of stream of symbolic data, all of the individual words. And what's a natural question to ask in that case is the entropy, or more specifically, the entropy rate of that word stream. So in other words, we're trying to say how much information do we have in the past words, in words we've already seen, about upcoming words, about the next word in particular. So if the writing is very repetitive, it should be very predictable. We won't have a lot of uncertainty, and so we should have a lower entropy. Likewise, if the writing is very unpredictable and very irregular, we should have a much higher entropy. And these notions of entropy, these are kind of the core ideas, the core entities that we interact with in information theory. And so a really important question is how to estimate entropies accurately given actual data. And that's a question that goes all the way back to Claude Shannon at the founding of information theory. He was looking at this exact problem in early 1950s. And he had this incredibly kind of ahead of its time idea, where one of the challenges of this estimation problem is that you don't just want to count up the words themselves and say, what's the most common word, the least most common, and look at the basic entropy, because it's actually the order and the sequence of the words that contains a lot of information. If I take a text and shuffle it, the overall levels of all the words are the same, but I've destroyed a lot of the meaning if I try to read it. And he recognized that, and he didn't have the computing power that we have nowadays. But in that paper, he had this amazing idea of actually asking people to make predictions about words, about upcoming words after being shown part of a text, and then trying to back out the entropy based on how often they would make the predictions correctly. It was almost like he's crowdsourcing the language model. And we do a lot of that stuff nowadays, but to write a paper like that in 1951 is just amazing. I mean, he was an incredible genius. But anyway, if you fast forward a couple of decades, there have been a lot of papers, and I'm going to in particular use this paper here from 1998, where they propose a a very effective estimator that incorporates that sequence structure. So it actually looks for the co-occurrence patterns of the whole sequence of words all at once. I won't quite get into all of the details, but essentially this estimate tells us how many bits we would need. This is one way to think about it. How many bits we would need to describe the next word given past words. And if that string of the words is completely predictable, we would need no extra information after we've seen the previous words. So we'd have an entropy of 0. And here is just like a fun exercise that I like to show to give a little bit of intuition and to kind of show how this is working, almost as like a sanity check. So here I've taken a couple of books and I've actually run through these estimators on the text. So I took a book from Hemingway, I took a book from Tolkien, Lord of the Rings, and I took a book from James Joyce. And then we have the entropies in bits over there. And Hemingway is very famous as a very simple and sparse writing style, and Joyce is the complete opposite. He's very famous for his complex prose, and you can actually see that reflected in these entropy estimators. I've also included the perplexity, which is just the exponentiated entropy. If you do a lot of natural language processing or computational linguistics, you oftentimes see perplexity measures there as well, but functionally it's measuring the same thing as the entropies. Okay. So social information. So how are we going to go about trying to take some of these ideas and apply them in the social context? Well, what we can do is essentially take the tweets that an individual posts and kind of treat them as if they were one of those books. And actually a typical Twitter user on, say, a one-year basis, if they're relatively active, they're writing maybe not a full-length novel when you glue all the tweets together, but like a novella for sure. And so we can take their kind of activity stream and just sequence all of that text and concatenate it together, and then estimate the entropy rates from that. So this is a study that we did that came out in 2019, and we developed a data set of about 14,000 Twitter users controlling for the language. So they were all English speaking according to Twitter. And we retrieved all of their tweets up to the kind of API limits. There's a lot of work on Twitter where you're working with a random sample of the tweets. This is called a garden hose. We used that to develop our initial sample, but then we went back in and backfilled all these users, because if you have this stream of text, but then you only have a 10% sample of that can introduce all sorts of problems when trying to run these estimators. So we're not looking at an enormous amount of Twitter, only these 14,000 users. But we have a fairly complete set of their public data for those users. And I'm skipping a lot of the details and the kind of heartache that went into this, but we did a lot of efforts to filter out bots and users that create an account but don't really do anything. There's a lot of work there, and bot detection is an ongoing problem, so it's not perfect, but we really tried our best to get a clean sample of about 1,000 users, and then for each of those users, their top 15 contacts on Twitter. I'm sorry, about 900 users. Okay, so here is what the entropy looks like. Excuse me. So this is the distribution of the entropies over our sample. It's pretty sharply peaked. If we did not use this fancier estimator, but we just looked at the more traditional notions of entropy, the Shannon entropy, we would be off by about 3 bits. So that actually tells us how much information is in not just the words themselves, but that sequence, that order. If you preserve that order correctly, how much more information do you get out of this? But it's useful kind of contextualizing these numbers and kind of quantifying what's going on. There's another very, very cool tool from information theory called Thanos Inequality. And Thano was a very famous and influential information theorist. And he kind of discovered this beautiful idea. Apparently, the story goes that he was giving a seminar or a grad recitation, and he got stuck on a problem. He made a mistake somewhere, and then as part of that, he found this inequality back in the 1950s. It's a very, very beautiful idea, and what it gives us is this notion of predictability of a bound on a prediction algorithm. Roughly, the idea is that if I have a data stream with a certain amount of entropy, and I have the best possible algorithm that I could possibly make at trying to predict those future words, how often will it be correct? That's this predictability, the probability of a correct prediction, pi, and that's bounded by Thanos inequality. So the best algorithm will never be able to exceed that, assuming you have a correct estimate of the entropy. And why this is nice for us is that we can start to make an argument about how useful the information is in this data without actually getting into machine learning and running actual predictions and making these language models. We can kind of come in from above more mathematically. And I think, you know, the machine learning has become so good recently and it's advancing so quickly that I think it's important to try to get at these bounds, because otherwise your claims might become out of date pretty quickly. So here's the distribution of that predictability using Thanos inequality. And here we can see that it's pretty sharply peaked at around 54%. So most users have a predictability of 54%. That sounds at first kind of bad. That sounds almost like random guessing, like I've got like a 50-50 chance. But you have to remember, this is correctly guessing the next word out of the entire vocabulary of possible words. And the typical user on Twitter has a vocabulary of about 5,000 words. So you're correctly guessing that one word out of 5,000 over 50% of the time. So there's actually a lot of predictability there. Now, of course, a lot of that predictability probably has nothing to do with the users. It has to do more with the structure of language and the regularities there. So we want to have certain controls for that. And I'll be talking about that shortly. Okay, another question about contextualizing this is kind of asking a kind of so what? Like, why do I care about being able to predict these words? You can actually, if you've built a predictive model, you can build kind of nice user interfaces and things. If you're familiar with Gmail Smart Compose, where it will kind of forecast the rest of the sentence ahead of time, and it's kind of eerie. It works pretty well. That's essentially like this applied problem. Is it actually built a predictive model? They're trying to forecast the words that you're writing. You also see this with smartphones. If you're typing on this, every smartphone is actually running character level prediction in order to get the keyboard to work. It's actually very beautiful ideas going on behind the scenes there. But for our purposes, I think that there's another way to interpret this notion of predicting these words. The idea is that if you're able to accurately predict these words, what you've essentially done is you've built a language model in the voice of that user, of that person. And once you're done that, if it's working well, you can, in principle at least, interrogate that model for the likelihoods or the probabilities that that person will say other things. So you can start to ask that model, you know, what is the chance that this person will write tweets about, you know, certain brands or sporting events or politics or whatever these kind of things are. That language model is kind of a profile in a sense, or it's like a proxy for a profile of that user. And so our calculations with things like Thanos inequality are essentially getting at a handle on how kind of, excuse me, they're getting at kind of how profilable the user is given their data. If they're just throwing a bunch of random words around, you're probably not learning a lot about the user. Whereas if they're very predictable, you're learning a lot more. Now you're not, there's an important kind of social science question here about, does this language model really act as a proxy for the user, or does it act as kind of a proxy for their online persona, which is really what's going on. They could be posting in very different ways online compared to what they actually are. But what we're really interrogating is kind of what's in that data. Okay. Yeah, so that's this notion of social information. Where does the information flow come in flow between individuals? Well, one thing that we can do, again, taking our cues from information theory, is to modify this question of entropy to look at what's called the cross entropy. So the idea here is, instead of looking at how much information we have about future words given our past words, we look at how much information there is about a person's future words given the past words of a social tie. So here I'm referring to them as the ego and the alter. So how much information can I infer about the future words of the ego given the past words of their alter? Does their friend contain useful information? Yes or no? And that becomes especially important when you get to questions about if that past information is redundant or not, given the ego's own information. And I'll get to that in a little bit. And when you switch from entropy to cross entropy, you're kind of this whole argument holds, except now it's not about their own data, it's about the data of their social ties. So from our perspective, or from my perspective, I want to ask, how much information are my friends giving the platform provider about me? That's what's captured by this notion of the cross entropy. And here's a plot showing the distribution in our data set of the entropy compared with the cross entropy. And what we can see is that there's a significant information loss, meaning there's a higher cross entropy than there is in entropy. And we can also see that there's a pretty diverse spread of how much information there is in those social ties. So here we're only looking at their most frequent contact. And we can see that unlike the entropies themselves, the cross entropies span more, a much higher range. And remember, when the entropy is measured in bits, you can almost think of this as a logarithmic scale. And so every time you increase 1 bit, you're kind of doubling your uncertainty. So there's like orders of magnitude spread there. Now, of course, part of this is explained by a diversity and how much information is actually flowing. And part of it is also that, your most frequent tie on Twitter might be very weak because you don't use Twitter very much. These were some of the things that we attempted to control for. But I think this is by itself an actually kind of very interesting lens in which to see and study individual Twitterers or tweeters. Now, of course, there's another wrinkle to this, which is you have more than one alter. It might be that there is information in the cumulative pasts of those alters that's not present in any one individual alter. And so we can actually adapt these estimators to handle almost like a joint distribution. It's not quite that clear, but we can look at this cumulative amount of information as we add on not just the most, the first alter, the top most contacted alter, but the second most alter, the top 2 alters, the top 3 alters, and so on. And here's a plot of this where I'm showing this cumulative cross entropy on the left, and then the distributions on the right as you add on more alters. And what you can see is as we go from the top alter to the top 2 alter to the top K alters, that distribution tends to kind of creep in and start looking a lot like the distribution of the entropy itself. Like I was saying before, this is kind of confounded by effects of language. There may be no information really about the users going on. It's just that we're learning a lot about the structure of English. Likewise, there may be confounding in this flow of information based on time. It's not actually that the 2 users are really talking to one another. There's some third event that they're kind of both talking about at the same time. And something like Twitter, this is very important because there's a lot of timely events, the Grammys, Oscars, pandemics, all of these real-time events are happening. And so those could be confounding these. And so what we did was we constructed some controls to try to account for time by randomizing time, and to account for social controls by looking at other sets of alters that are tweeting at a similar rate at similar time periods. And all of this is using real data. We've never tried to look at randomly generated English or anything like this. But whenever we move to one of these controls, when we break the actual ties of users, we see a much higher cross entropy, meaning there's much less information. And even though as we accumulate more of these kind of pseudo alters, we do gain information, that's kind of the effects of having more data. It never gets down to the comparable level of the actual cross entropies that we see. And here is the same curve showing the predictability instead of the cross entropy. Now, if you remember from before, we found that the typical predictability of egos was around 54%. And if we add that on, we see something here, which is a little surprising. It seems like if we have enough alters, we can actually do a better job at predicting the ego than if we looked at the ego. There's kind of a paradox there. And the way to think about this is that orange curve isn't necessarily what you want to be looking at, because yes, there may be a lot of information there, but in principle, all of that could be redundant if we also had looked at the ego. And so if we include the past of the ego as well, we kind of resolve that paradox, and we actually see how much extra information or extra predictability there is amongst those alters on top of what you would already learn from the ego. And we can see it's, on the order of 6% or so. I think I've got some numbers coming up from that in a second. Now, we only have a data window in our sample of about 15 users, so we can't really look at someone's entire social network. But one thing we could do is we could extrapolate these numbers by fitting a nonlinear saturating function. And if we do that, we can actually measure, what this kind of quote unquote fundamental limit of predictability is. And for the orange curve, it's about 60%, 61%. But of course, people don't have an infinite number of friends. There's going to be a kind of upper bound to how big your social network is. And one argument for that upper bound is what's called Dunbar's number, where they they looked at the structure, the size of the human brain to take an estimate of that the typical social network kind of caps out at about 150 ties. And if we see that, we're actually pretty close to saturation already if we compare 150 versus that limit. And if we consider the blue curve, which is kind of akin to a transfer entropy, if you're familiar with some of that, we can see that the number is a bit higher. It's about 63%, 64%. And the ratio between those two numbers is right around 95%. And I'm going to get back to that in a second when I discuss a little bit of the implications of this. I hope I'm okay on time. I mentioned those data-driven studies of information flow, and that's kind of what our first project was, our first paper. But there's also a lot of modeling that goes into the spread of information, the spread of ideas. And we came up with a model that we're really keen on that we call the Quota model. The name is pretty clever, I think. It's a play on voter models, if you're familiar with that. But it's essentially a toy model, and it's trying to improve on existing modeling efforts by getting a little bit closer to the data. So the idea is like, yeah, you can run a disease model and capture this, diffusion of this disease on say a social network, but holding an idea or holding an opinion, it's not really the same thing as a disease. I think that's a very useful analogy, but you can take it too far. The cognitive biases that we have as we encounter ideas it's not really the same as like an immune system. And likewise, the notion of ideas and adopting something and being exposed to these ideas, they're not always well captured in the data. If you just have a bunch of tweets, it's really hard to go beyond things like keywords and those structural measures. So the idea with the Quota model is we introduced a model that's a little bit closer to the data by actually modeling conversations. So the idea is that each individual on a social network, on like a synthetic network, is emitting words at random. They've got some vocabulary and they're just drawing words at random. It's a very simple toy model. But every so often, instead of drawing words from their own vocabulary, they look at one of their social ties and they quote a little sequence of some of their words. And I've kind of illustrated a little thing here. So a little toy example might be that, the alter says something like, hey, let's go to the beach tomorrow. And the ego responds, it might rain, so let's go to the movies. It's not really about a retweet of the entire, you're not quoting the entire text that your alter is saying. It's just those little function words, those little phrases. Let's go to the argument here is that the more often there are those little quotes, the more likely it is that a person's listening. Of course, you could have the exact same conversation without quoting that little segment of the text. But the idea is that on average, on long conversations, there's probably going to be more information flow if more of those little quotes occur. And in our little toy model, we have a parameter Q, which essentially controls how often you quote a neighbor versus how often you generate your own text. And then once you've simulated this model, you have these text streams that they're nowhere near the complexity of real data, of course, but they're actually much closer to the kinds of data that you would get from something like Twitter in terms of actually being, symbolic data streams. And what's nice about this is you can put together little toy motifs, little proxies for different network topologies, and you can see how information flows. So here, for example, we have a kind of line of individuals. We can almost play like a telephone game, and we can actually study how information attenuates from the beginning to the ending of that line. So we had a nice paper that came out in Chaos where we looked at different topologies and graph models and looking at the spread as a function of these parameters. And something we found in that paper that we thought was interesting enough that we wrote another paper about it was this notion of density. And density usually promotes the spread of a disease or of an idea, that the more links there are, the more opportunities for spreading. This is what social distancing is all about. You're trying to cut those ties so the disease has less opportunity to spread. What we found in our Quota model is actually that there's less information flow when the network is denser. That phenomenon also occurs in a model of social information flow called complex contagion, and this is where the disease, the probability that you adopt the disease or that you become infected increases the more times you're exposed. So you kind of have to see the idea from your friends more than once in order to get exposed to it. And that's been proposed for a while as an alternative to these simple contagion models, specifically for capturing more of the notions of social spreading versus disease spreading. And what's interesting about that is for complex contagion, you have to have that mechanism called social reinforcement, that the idea has to be seen by from multiple sources before it starts to kind of break through to you. We don't have that mechanism at all in the Quota model, and yet we see a similar effect. And we've got on the left some simulated plots showing this in different views, and on the right we have it in real data sets. So that's pretty cool. And also mathematically, what I was really keen on in this model is that it's simplistic enough that it's actually analytically tractable. So we came up with some expressions for how much we would expect the entropy to be on a tie between an alter and an ego as a function of their individual languages and how often they're quoting one another. And it's an approximation for what's going on, but it actually works pretty well. There's pretty good agreement here. You can see in the plot on the left that we are underestimating the cross entropy by a little bit, but I'm actually pretty happy with how good. At least it was good enough to get the paper accepted, you know. Okay, so I think I'm doing okay on time. So I have one other quick thing I just want to show as a little bit of a preview. This is some new stuff. I was hoping to get this up on the archive this week. It'll probably go up on next week, but this is kind of a related question I've been looking at on temporal networks. The idea is essentially how the idea in his previous studies were how much information do your friends say about you? And there's a lot. A similar question you can ask in a temporal network is that if I can see all of the activities from your individual social relationships, I've got a lot of information. But if I can't see those different activities, I can only see the overall activity. Can I somehow back out that individual activity? So if in this case, you can imagine I have a time series for every link in the network, and that's what's shown in the left on blue. If I'm not able to see those separate signals, but I'm only able to see the overall signal, say I have an app installed on that person's phone, or I have some sensor where I can measure their overall activity, but I can't really see the social ties. Can I somehow like demux that node signal into the edge signal? And what we found actually, excuse me, is that if you can sort of through side information back out the network topology, you can actually do a really good job. At least I thought it was a surprisingly good job at recovering those individual time series per edge, which is somehow the more fundamental information for the temporal network, just looking at the node information, even though there's much, much less data in the node activities than there are in the edge activities. And we can see that in these matrices on the right. I've actually drawn them to scale. The nodes, there's about 4 times fewer nodes than there are edges. And this has all sorts of interesting implications where you can look at those activities and actually kind of back out the weights on the links in the temporal network and back out things like what's called the multi-scale backbone, which is kind of like the most important links in the network. And so it's useful for a lot of downstream tasks. And again, I'm being a little bit vague because we haven't quite published any of this. but I'm happy to talk a little bit more about the details of this, and there'll be a preprint in maybe early next week. We're almost there. Okay, so last little bit, I want to talk a little bit more about some of the implications of our studies. If you recall, when I looked at this curve, I said that the ratio between the blue curve and the orange curve was about 95%. The difference between those two, what I call the information gap, the fact that it's so small, I think is actually pretty important. It has some important kind of privacy implications, because it means that if I don't have access to the ego's data, but I've got good access to their social ties data, I also have good access to the ego's data. I can come close to building a language model, at least in principle, for the ego, just from the alters data, and I'll be within 95% of that original accuracy if I had everything. So the idea, of course, then is like if I opt out of a platform, say Facebook, not to pick on any particular platform, but if I don't use Facebook, but all my friends are using Facebook, in principle, that language model is still there at Facebook, kind of latent, sitting amongst all of those social ties. And that has potentially privacy implications. If you're concerned about a platform and you don't want to use it, but your friends are using it. It's kind of like a rising tide lifts all boats, and a rising social network breaks all privacies. But of course, in order to do that, even though the data is in principle there, Facebook, they'd have to have the AIs to pull out all that information for the language model, but they'd also have to know about the social ties of this person who's not a user, right? If I don't use Facebook, how are they going to know who all of my friends are? Where does this kind of side information for the social network come from? And when you start thinking about this and thinking about how these companies work, there's actually a lot of extra information that they can bring in. They can do all sorts of things, scraping public records, property records, public tax records. They can buy advertising profiles, so political mailing lists and things. I don't know how it works in the UK, if there are privacy protections, maybe things like GDPR. In the EU, but in the US, there's the political parties. They put an enormous amount of effort into building these profiles for people. Social media platforms can buy access to a lot of that data. Also, a platform can build tools that can request access to user data outside of their own. So, for example, a chat program might ask for access to someone's contacts, and there's a good reason for doing that. Actually, if you sign up for Twitter, you want to get friend recommendations so you can start following people. The Twitter can look at your address book and say, oh, these users that you already know are also on Twitter. If you want to start following them, here they are. But of course, once they see your address book, then they can see who all of your other friends are, and they can again start to back out that whole kind of shadow social network. And actually, a lot of people are studying this idea of shadow profiles. There's a lot of really cool papers on that. But there's even more sources of information. So for example, users on the platform could actually be actively providing signals about non-users. So for example, here's something where someone is interested, oh, I wonder what my niece is doing. They want to look them up on Facebook or on something like this. So they could actually go in and type in the name of their niece, not knowing that their niece actually doesn't use Facebook. So, but now Facebook, and again, I'm picking on Facebook. I don't want to single out any individual platforms. Now Facebook would have access to, okay, this user knows someone or is interested in someone called Alice Smith. Let's, start to aggregate that. And again, another way where this can come through is all of the image recognition and, face detection that is happening. Essentially, a platform can run through facial detection algorithms on all of the photos that are being uploaded and recognize all the faces and start to cross-reference them. So here's a little kind of cartoon example I put together with some celebrities. You run your computer vision on all these photos and you start to recognize all of these users. You see that there is some mysterious person. You don't recognize that face, but you do see that it's the same face across all of these different photos, and you keep seeing this co-occurrence. You can start to build in, whoever that is, we can start to see those connections. And this might sound a little bit like science fiction, but it's not. Like I was saying before, Facebook runs all of their photos through all of these deep networks all the time. And this is essentially close to a solved problem, I would say. So that's maybe a little bit outlandish compared to buying access to property records, but it can be a little surprising just how many avenues there are open to these platform providers to get access to non-user data. And then, of course, once you start to learn that, we recognize that this mysterious person is connected to all these other people. We could then maybe start to profile them somewhat by looking at the activities of those people that we do have. And again, our study was all in theory and in principle because we were using these information theoretic tools. It may be the case that actual machine learning tools are not able to do that. But I do have a feeling that given how good these tools are getting and how much they're improving, that this kind of stuff could occur. Okay. So in summary, I think I'm okay on time, but what we've been doing is trying to get at good non-parametric measures of information and information flow that incorporate more of the language data and also more of the temporal information. We're always trying to predict future words given past words. And I think that's a very important distinction to make. We also introduced a new mathematical model to try to get a better study to complement existing work by getting a tractable model that's a little bit closer to what the data actually look like. And what we found is that there's actually in principle a lot of information in a user's social ties. And that if a platform can back out the social ties independent of the user's data, they can start to build these quote unquote shadow profiles. If you're interested in the papers or if you're interested in seeing more, you can hear some references, and all the papers are up at my website, bagrow.com, just my last name.com. And like I said, I'm hoping that that new study that we have on temporal networks will be up shortly. A couple of quick acknowledgements. I really want to thank my collaborators, Lewis Mitchell, who's faculty at University of Adelaide, and my two students, Sipei Liu and Tyson Pond, both here at University of Vermont. Fantastic, really working with them. They were really key contributors to everything. I'd also like to thank the NSF, who supported a lot of these studies, and I'm currently running a team that's supported on a gift from Google Open Source. And I want to mention that because the focus of those studies is not really what we're talking about here, but I just wanted to mention it in terms of disclosure, because Google and Gmail, they're also kind of mixed up in all of these things. Google is another company where a lot of people have privacy concerns. They had no say in any of these studies or any of this kind of stuff. But just in the interest of transparency, I wanted to mention Google. Okay, so yeah, thank you very much.
Thank you so much, Jim. It was very inspiring. So now we have still time for questions. So you can write down your question on chat or just unmute yourself and make your question. So I want to start with a question. So how much did you analyze, like, what is the importance of context here? Like, for instance, if all your history of your friends, what is it been talking about in your data is about pandemic, how well could you predict about politics or something like that?
Yeah. So that's a really good question. We didn't get too much into those details. The estimator, we just kind of used it on the entire data set all at once. There is a drawback to that language estimator, the Cantor-Yannis estimator, which is that it needs a lot of data in order to get a good estimate of this quantity lambda, which I didn't talk about all those details. So I'm sorry if I went a little bit fast, but you need a fairly long amount of words in order to get a good estimator there. So it's not really something that you could use in real time if you want to understand, real time events. Now the pandemic, of course, has been going on for so long that we would have a lot of data, unfortunately. We do have a project spinning up at Adelaide that Lewis is leading. I actually totally forgot to add the slides on this, but there's a call for a postdoc. So if you're interested, let me say, if you're interested in actually working on all this, we have a position at University of Adelaide for a postdoc in studying this exact problem. And he's very interested in that exact question that we're going to be looking at, which is politics and information, between people from different political affiliations, and how do events kind of try to tie into these things. And I think we need to work on better tools to work at that are less data hungry, essentially. But yeah, it's a fantastic question, and we really just scratched the surface.
Ronaldo.
Hi, Jim. Thanks for the talk. I'm interested in the Volta model as a way to measure. I mean, I don't know if maybe I missed when you spoke about this, but the measuring of divergence of the information, right? Because I mean, I can quote someone and change a little bit of the story.
Yep.
And when does the story that I'm now telling is really no longer represents the original source, right? So if I quote and quote and quote in this chain, I mean, do you think? I mean, because this can be linked to your motivation on fake news and disinformation, or something, which might emerge, I guess, more natural. So it's not that I'm actually lying, but I just added, I guess, a word. But if everybody does this after chain, it no longer represents like that. Those the game that we play when we were kids or something, right? So like
the telephone game. Let me see if I can go back to. Yeah, so that's a really good point, actually, and that's exactly something that we're trying to capture here in the quota model. The idea with the quotes is it's almost a little bit of a misnomer, because it's not like you said this entire statement, you know, here's 200 words and I'm making a copy of that. It's really just in the process of me writing my own 200-word statement, I'm going to quote little, you know, 3, 4, 5 word segments of that. And that was, again, just trying to get at this little here, that this notion of these little functional phrases going on within the broader statement as this measure of communication. And it captures this telephone game idea perfectly. We can actually see, as you move away from the head, from the original source of information, you lose information. You get this growing cross entropy the whole way through. So it captures that attenuation effect really well. And I'm optimistic there could be some connections with misinformation and all these things, but it's a very coarse idea, you know, these kind of random streams where you're just kind of having these little copies. It's very much a toy model. And I think if you want to incorporate things like lying, or, you know, those actions of misinformation, you know, I think the management sciences, they talk a lot about what's called strategic ambiguity, which I think is a really nice way of saying lying. That's a little bit more subtle, because there it's like you're very much intentionally going in and massaging words and saying these kinds of things. So I would be reluctant to push the quota model too far in those directions, but I am hoping that this kind of stuff could start to get us there, because, you know, in a disease model, there isn't really this notion of strategic ambiguity. I think that communication is a little bit more complicated. And so I'm just trying to seek out, like, what is the simplest model possible, but not too simple. Yeah. So it's
very nice. I was thinking in terms of, if you have this function that describes the attenuation, right? So a deviation from that can perhaps indicate somebody messing with the information in a way that's not what you expect in a natural way, in a sense.
I see. Yeah. So you can treat this as almost like a null model, and then see for either excessive information flow or excessive lack of information flow. And I think there's lots of really cool stuff, and things like information silos. This is something that we're thinking about as well. Yep. I see what you're saying. Yep.
Thanks.
So a related question to this, Marcus just posted on the chat, like, if your words are not necessarily words, but somehow a token representing an event, could you use this to make the next event?
Yeah, so the idea there is to essentially lift away from the actual words as just discrete symbols and go to something like contexts. And the idea, if you're able to do that, you could run the exact same methods through. And one area where that might be useful is to do these word embeddings, where you represent each word with some semantically meaningful vector. And then you can essentially look at it. And there's a ton of research in natural language processing on these methods, and trying to understand sentences through these sequences of vectors. And I think you could then start to connect those to these information theoretic measures. Yep.
Equal.
Hi. Wait, can you hear me?
Yeah. Yep.
Okay, cool. I know we've got some questions in the chat, so Diogo, you know best. Thanks for the talk. My question is about one thing you mentioned in multiple points. I mean, as someone working on information, you use a lot of metaphors. And you've said at some point, even you said that holding an idea, holding an opinion is not the same as a disease.
Yep.
But you also spoke about the infodemic.
Yes.
And these epidemic metaphors to information,
Yes.
they're as old as the 19th century at least. And my bet is that people, at least in popular culture, are going to carry on using them because they're easy to get. On the other hand, you pointed out like complex contagion and things like that. And the more we dive in, the more we know that actually the viral or epidemic or whatever is a poor metaphor. So what do you think a researcher should do in that case? Like, because you stand in this between like explaining something in an easy way and kind of trying to get at the detail.
Yep.
How do you address that? I'm curious because I face the same problem.
Yeah, I mean, so I think that you're speaking my language. That's exactly what I've been thinking about with all of these things. I even remember seeing, I think on the WHO, the WHO page, where they started talking about the infodemic, and they had some phrase that was like, we need to vaccinate the population against misinformation. And I was thinking like, well, what is a vaccine in this context? And, you know, it raises like this kind of specter almost of like mind control. And yeah, I think that the analogy is just getting stretched too thin. And yeah, how to combat it? It feels a little bit like the horse is already out of the barn, you know, to use another analogy. I think that information theory is one direction here to kind of look for scenarios where the analogy makes one prediction, but reality contradicts it. And then kind of use that to kind of try to structure a better understanding. And I think another approach to this with the research is bringing the data and our methods or our kind of methodological understandings closer to one another. Because again, like, how do you go from a bunch of data to these notions of ideas? It's pretty hard. One tool for that could be something like information theory. But of course, you know, the information theory is about like uncertainty and the lack of uncertainty and all this. And it's not, it doesn't get at all the kind of philosophical implications of information, and it is unsatisfying in a non-mathematical sense. Yeah, I think that you know, if you can come up with cool phrases for things, you know, that one study that was called the Disinformation Dozen, like that was just amazingly memorable. It's this great kind of alliterative argument. It's very memorable there. I think if we could come up with language along those lines that's getting away from, you know, pandemic and disease outbreaks and all these things, I think that would be valuable. But at the same time, I think it's going to be a really hard fight because those metaphors and that kind of analogical thinking is already pretty firmly embedded.
One last question here in the chat. So it's about how do you map the dynamics on social network, like how the information flow is updated if you create new ties and break new ties, how this is affecting in your model? Yeah,
that's a fantastic question, and we haven't looked at that in our data at all, I would say. So the idea is essentially like when a new social tie comes in, or when an ego gains an alter, how does information adjust overall? Does information kind of lower? Is this person making things noisier? We got at a little bit at those questions in our second paper and the 2020 paper in the Quota model, though not in the real data. But this is something that I think we're hoping to do, Lewis and I, with this new postdoc position, is to look at you know, information from the alters to the ego and information between the different alters, and then as the social network is changing. So I have an unsatisfying answer in the sense that we haven't really looked at it yet, but I have a satisfying answer in the sense that I think that's an excellent question.
Thank you, Jim, so much.
Yeah.
We have the question, but we run out of time. So
yeah.
Thank you. If you want to, you can contact Jim to follow up with his questions.
Yeah, please do.
And I'll make this presentation available at our channel on YouTube. Is that okay, right?
Yeah, perfect.
Thank you.
Yeah. Take care, everybody. Stay safe.
Thanks.
Bye-bye.
Thanks, Jim. Bye.
Thanks. Bye.